Okay, okay. So no problem. Okay, we are covering basics only. They are like just
No,
ABCDs.
sorry, sorry, just one question.
Yes, please.
In here, 5 is your T or your D model over here?
Five is your T.
5 is your T. So,
Yes. Okay, like I am going home today. This is your T. Size is 5. And D model is 8. It has got 8 dimensions. But we are considering row vectors. Okay, because they are following the same in PYQ also and in the PYQ, this GS also. So this is your 5 into 8. Is that okay?
got it.
Okay. So
Sir, let
now,
me ask about attention weights. It's after taking the softmax, right?
yes, so this is the attention matrix. I was covering the size. So you take softmax of this score, so you'll get the attention matrix.
Yes. Okay.
Okay. And now from here, what will be your output now? Output will be is equal to, let's call this as attention matrix only. Attention matrix into V. So this will become 5 into 5 into 5 into 8. So your output size will become 5 into 8. Is that okay? So we have passed through the attention layer. We gave 5 into 8 input and we have got output 5 into 8. Is that okay? And this was
Yes,
in the
sir.
case of single head. So here the parameters will come. For example, they might ask the number of parameters. So parameters we have got for WQ, WK and WV. So this is 8 into 8 into 3. Is that okay? Now here only, once you get this output, you pass through a linear layer, WO. This 5 into 8 which is we have got, we pass through WO and size of WO is also D model into D model. So we again get 5 into 8 size. So our parameters WQ, WK, WV, WO is equal to become 4 into 8 into 8. This 4, can remember, this will keep on changing. It is 4 into D model into D model. And if you have got, some more number of heads also, these number of parameters, they remain the same. And I will just explain why they remain the same. Suppose you had 4 heads. 1, 2, 3, 4. And we pass 5 into 8. So what happens? Here, it will have WQ, WK, WV. This will also have WQ, WK, WV. They are different. WQ, WK, WV, WQ, WK, WV. The size of them, it becomes D model into D model divided by number of heads. So this will become how much? 8 into 2. This will become 8 into 2, 8 into 2, 8 into 2. And the output from this head will also be 8 into 2. And finally, we concatenate that to get 8 into 8. Is that okay?
Yes, sir.
So in this also, when you calculate the number of parameters, so here it will become 3 into 8 into 2 plus 3 into 8 into 2 plus 3 into 8 into 2 plus 3 into 8 into 2. And if you take 3 into 8 common, so this becomes 2 plus 2 plus 2 plus 2. So it becomes 3 into 8 into 8. And
This 3
finally,
is batch size, correct, sir?
3 is the WQ, WK, WV. It is not the batch size.
Oh, number of parameters. Oh, okay. Yeah,
Okay.
makes sense.
And finally, you pass it through WO. WO is always D model into D model. So it becomes 4 into D model into D model. So this is a tip that whatever the number of heads are there, you can calculate the parameters in attention layer directly by using this formula. Is that okay?
Also, sir,
Yes, sir.
W doesn't have any biases, right?
Yes. I covered na nn dot parameter. So we are initializing them nn dot parameter and dot parameter like dot nn dot embedding. It is also wrapper around nn dot linear and it does not have biases.
So, any particular reason for not having biases? Because WO is also a simple neural net, right?
So like I covered earlier, all those questions we'll leave again for later on after the quiz. We'll
Okay.
focus on the quiz part. Okay.
Okay, okay.
Okay. Okay. For that, okay, we will discuss with Laveen. He has got far more knowledge okay, than all of us. Okay. So we have covered embedding matrix and we have covered the attention layer. And here we got parameters walkup size into D model. And here we realize that the parameters are 4 into D model into D model. So this is the directly we can calculate. Okay, without going into the architecture. Now this output which has come 5 into 8, T into D, 5 into 8, we pass through feed forward neural network, FFN. FFN size will be given and this attention layer, this for example, this is the attention layer. This is the part of encoder layer. This is the encoder layer. So you might have seen in your PA1 and PA2 that first we defined this and then we wrapped it under the encoder layer. This FFN size will be given to us. For example, in this case, if I take, for example, 64, then what happens that this 5 into 8 which is there, this is 8, this pass through this feed forward network, size is 64, and this FFN which is there, remember this, in this bias is there. Okay, in FFN bias is there. For the first time, bias is coming. And here, why do we are doing the feed forward network? Because we want to bring non-linearity. So we apply here ReLU or GeLU, whatever is there. So here, if you see the number of parameters will become 8 into 64 plus 64. This will become 64 into 8 plus 8. So these are your number of parameters in FFN. Is this clear, everybody?
Yes, sir.
Okay.
And
So
sir, one quick note on that, like
yeah, yes, please.
in the feed forward neural net now, in the middle layer or hidden layer, we have number of neurons that is demodel into 4.
D model into 4, like the professor he had covered here, basically for the GPT
Yeah.
and the BERT example.
Hmm.
But it is not necessary that your FFN will always have 4 into D model.
Okay, I thought it's general, like generally we choose demodel into 4.
Yes, okay. So it is not general, it can be
Okay.
chosen. Or in the question,
Hmm.
Mali, don't assume that it will be 4 into D model. Please look for the FFN size.
Okay, sir.
Okay, they might give you 128, they might give you 64. As a concept, okay, we should understand that why we have brought FFN. FFN we have brought to bring non-linearity. Okay.
Okay,
And
and non-linearity has been applied in the hidden
yes,
layer,
in
right?
the hidden.
Okay.
And in the WhatsApp group, okay, Loveleen had explained that why do we have biases in the FFN? Because when we apply non-linearity and it's like a ReLU, then everything which is there, okay, 0, it remains 0. So that's why that is one of the reasons that we apply bias in the FFN.
Okay, so make it a positive number.
Yes. So now we have got in the parameters. So we are going.
Sir,
Yes.
so before feed forward network, we have layer normalization. Sir.
That I will cover. That I will cover.
Okay.
So first, okay, I covered this part, okay, and just now I was going to cover that, okay. You prompted.
Okay.
So we have covered embedding layer, we have got attention layer, and we have got again now FFN layer. Okay, and we have also got a tip that irrespective of number of heads, we know that number of parameters will be T model into T model. Okay, here it will be walkup size into T model. Here it will be D model into FFN plus FFN size and FFN into D model plus D model size. This will be the parameters for FFN. So this we have to remember. Now we come to this layer normalization, which just covered. So we gave one input here. This was the input. We passed through attention layer. We passed it through feed forward network, FFN. So basically, to allow the gradients to pass, we apply this layer norm. So what do we do? Whatever the output we have got from the attention layer, we do one normalization here at input also, like we used to do in the deep learning. And then we do here also. So we add the residue and do the normal this. So for example, if I have got here x, so what I will do, x minus, what we do, x minus mean minus mu?
Mean divided by the standard deviation.
This, okay. X minus mu is x dash. And then we define a new input or the norm, which is gamma into x dash plus beta. So these are again the new parameters. And size gamma and beta are equal to your D model. Okay. So one we are doing here, and again we do for the FFN. Is that okay? So for the encoder, for each layer, you will have D model plus D model, 2 into D model. You can say that. Is that okay? 4 into D model. It's a shortcut.
Right.
This is layer norm.
Can you explain that again, sir? How it's 4 into
Okay.
D model?
We applied okay, one here. So formula is gamma into this normalized one plus beta. This gamma size is D model and this is also D model. So here the number of parameters here will be 2 into D model.
Okay, sir.
Again,
And
we
after
come
the FFN
also
we have another layer normalization.
again it is D model. So 2 D model plus D model becomes 4 D model.
Okay.
Okay. So this is your encoder layer. So we have covered all the parameters. In case they say that there is a output layer also. So for example, if we have got a pure encoder we have got, for example, GPT. So here we have got a size of 5 into 8. But in the output layer, to find the probability distribution, we have to find the probability distribution over entire walkup size. So the size of this output layer will be what? Again, walkup size into D model. Is that okay? Then only we get 5 into 8 into, for example, D model is 8 into 20. Then only we'll get an output of 5 into 20. And then only we'll be able to do the probability distribution over that.
GPT is decoder, sir, right?
Oh, sorry, decoder. Yeah. But I'm saying this, for example, in our PA1, if you realize, we were
Yes,
given
yes.
output layer also.
Yes.
Okay. So if we are giving that output layer, so finally, what we have got again, now we can summarize from the PA1 example only, parameters of your embedding matrix, embedding layer, and output layer, they are same. So this we can write as 2 into walkup size into D model. Then we come to, yes, please.
Yes, sir. I have a question. Like, how the output in the output layer, the embeddings is getting like trained.
Okay, okay. So this again, I'll just cover again once we come to GPT. That's
Okay,
okay.
okay, okay.
Okay. So I'm just covering the parameters part so that if a question comes to calculate the parameters, then we can calculate without any doubt. Is that okay?
Okay, sir. Okay.
Okay. Now in attention layer, it is 4 into D model into D model. Okay, you don't have to care about anything about number of layers, 12, 8, whatever. Okay. Then your FFN, we calculated D model into FFN plus FFN, FFN into D model plus D model. This is this. Now only the layers will count for your layer norms. So layer norm parameters will be 4 into D model. So if there are 12 layers, then it will become 48 into D model. So these are, and then we come to output layer. So this we have considered here only. So these are the total number of parameters in an encoder. Any discussion on this? Any variation? Any discussion on this part? Anyone? Ganesh, any
No,
input
sir.
on this? Ganesh, may I request you?
Yeah, I may not be able to talk and may leave in between, but so
Okay.
far going very great, and you have summarized it very well, and especially the confusion around the heads in the attention layer and all that has been very nicely explained. Thank you.
Yeah. Thank you, Ganesh. Thank you. So shall we go ahead again, friends?
Yes,
Abhini?
yes.
Okay. Okay. So now we will come to the decoder part. And once we understand that this encoder and decoder, then understanding GPT and the BERT will become much more easier for us, for all of us. So the decoder part, how does it work? So decoder has got, I will first draw the decoder full architecture. So this input has come, the output of the encoder has come, and the, let's say its dimension is T into D model. Okay. This was a different language. For example, we are doing translation. So I was saying I'm going home today. But when we translate to some other language, it might become long. मैं आज कर जा रहा हूँ. So there I had 5, but here how many have become? 1, 2, 3, 4, 5, 6. So this, if you remember in a PYQ, T1 and T2, this T1 is the token size of the encoder. And here in the decoder, we have got one start token also. So this is a start token. So this T2, which is there, it has become now 7. Okay. And what do we do in decoder? I will cover first the parts. So first is the mask attention head layer, MHMA. Then there's a cross attention layer, MHCA. And this has got now FFN. And this is the decoder layer. And then we pass it through output layer. So decoder always decodes stepwise. For example, I give start, I have written, I give go. So this go which is there, its dimension is how much? Again, for example, 7 into D model. So I write again 7 into 8. Is that okay? So this 7 into 8, okay, it will pass. And it will give an output here. This is the probability distribution over the vocabulary. And I know that here it should be may. The first word should be may. In second, I pass मैं. Then I'm just writing. I will explain everything. घर जा रहा. Okay, we'll delete this. So this I give input to the decoder. So when the decoder is decoding this go, he does not want to see all this मैं आज घर जा रहा हूं. When at the second time step, this every output is fed sequentially into the decoder. So this may will come here if I'm doing the teacher forcing. So when I'm feeding may, I don't want to see any information about these future words. So how do we achieve that? That is the basic objective of mask attention head, this mask head, which is there. And how do we do that? Now we just enter MHMA. Okay. So this is the MHMA. In MHMA also, so out my input is now 7 into 8 input I've given. It has also got WQ, WK, WV, and again it will have WO also. The size of this, irrespective of number of heads, like I covered in the encoder, here the size will be 8 into 8, 8 into 8, 8 into 8, and WO also will be 8 into 8. First we calculate Q. So Q will become input into 7 into 8 into 8 into 8, size 7 into 8. K becomes again 7 into 8, and V also becomes 7 into 8. But something we do here in the Q and K. What do? We find the score. Score when we find, it will become 7 into 7 like encoder. Any doubt on this? Any question?
No, sir.
Okay, very good. And these scores, what do? We have got another matrix. So this score matrix is 7 into 7. And it has got some numbers here. We add this matrix with another 7 into 7 matrix, which upper part contains minus infinity, minus infinity, minus infinity. So what happens when we add this entire part will become minus infinity, minus infinity, minus infinity, minus infinity. And now when we have taken the sum of this, so I say this is score 1 when I've taken. Now I find attention matrix is equal to softmax of this. So when you will find softmax, you know e to power minus infinity, what it becomes? It will become 0. Okay, very nice. So all these values which are there in attention matrix, I'll copy this only. So your attention matrix here now will be, this will become 0, 0, 0, 0, 0. And as you keep on progressing, you start paying attention to other words also. So effectively what we have done, that when we pass this, मैं आज घर जा रहा हूं, we passed it total, but when we considered this go, I did not pay any attention to मैं घर जा रहा हूं. When I passed मैं, I did not pay any attention to आज घर जा रहा हूं. When I came here, I did not pay any attention. So this is the mechanism and how we carry out masking. Is that okay? Any question in this? Suraj?
It's clear, sir.
Okay, very nice. Okay. So now we have.
Sir, can you explain again? I was just.
Okay, no problem. So like the encoder part, we have got WQ, WK, WV. Size will be demodel into demodel. Is that okay? And we have got WO.
Yes.
Now I pass this go मैं घर जा रहा हूं. Now, in a decoder, unlike an encoder, I passed everything. I wanted to have the semantic relationships between the words and the positional relationships. I did all that query key and value. I got some input from the encoder, which is carrying everything. But in the decoder, when it generates words one by one. Okay, so this is one token. So it is generates token one by one. So Go will generate one token. When I come, I feed this, what has been generated here, it will generate something. So when I'm generating here, I don't want to know what are the words which are ahead of me. I don't want to pay any attention to that. And how to do that? What do? We use the same concept. We find Q, K, V, but after the score we find score is equal to Q into KT divided by root DK. So we get some scores. So we have got some scores, for example, 0 0.1, 0.2, 0.3, 0.1, some values they have come. We add a matrix which upper half contains only minus infinity. So here it contains only, this will contain 0.1, or it will contain 0, rest is minus infinity. This is 0, 0, rest minus infinity. 0, 0, 0, minus infinity. 0, 0, 0, minus infinity. When you add this to this matrix, what happens? Any number which you add to minus infinity, it will become minus infinity. Is that correct? Oh.
Yes.
So this converts to minus infinity. And here we are adding 0. So all these numbers which are there, they are retained. Is that okay?
Yes. Yes.
And now when I pass through the softmax, so when I take the softmax of the score, I know that E of minus infinity is 0. So all this E minus infinity values, they will become 0. Is that okay?
Right. Right. Yeah.
Yeah. So see, this is Go. So this is Go. So I am having only this information. This is Main. So Main has seen only Go and itself. Ghar. So it has seen only Go, Main, Ghar. So as I proceed, I am not paying any attention to the future words. That is the concept. Is that clear now?
Yes. Yes.
Okay. Okay, very good. Okay, so now from here we have come out of MHMA. Okay, so this was the attention matrix, and then we get output from this. For example, I call S is equal to this, whatever I got attention matrix here, into V. So this will become 7 into 7 into 7 into 8. This I will get an output of 7 into 8 output. Okay, so we have covered this part, MHMA part. This is the MHMA, and here I have got S. Size is 7 into 8. This I call R, the input from the encoder. This, for example, was I'm going home today was 5 into. Now we enter MHCA. This is multi-head cross attention layer. So here I want to take the input from the encoder also. So conceptually what I have done, I have found the semantic relations between the words without paying attention to the future. I have done the same thing which I was doing in encoder, but I did not pay any attention to the future words. Now I want to pay attention to the encoder input also, because it has given me some input. So at MHCA, again I have got WQ, I have got WK, I have got WV. The size of these are again D model into D model. So this size will again D model into D model. Before I proceed further, I will mention here, so we can write parameters in MHMA. Kitna hoga? How much? 4 into D model, irrespective of the number of heads. Is that okay?
Yes.
Okay, so don't consider the number of heads, just you can directly calculate this number of parameters. And in MSCA, what happens? you calculate Q which is there. This is S into WQ. You are taking the decoder output. to
So the
calculate Q.
mask is constant in the mask attention layer, sir.
Yes, yes, it is constant.
Okay.
Okay, so you have given the MHMA. It only depends on the token size, because depending on the token size, you will form that matrix.
Okay, sir.
Okay. So now this size will be how much? S size is 7 into 8 dot 8 into 8. So I have got a size of 7 into 8. The key value which is there, I utilize R, the encoder input which is coming. So this becomes R into W K. So this will become 5 into 8 into 8 into 8. This will become 5 into 8. Now score will become what? Q into K transpose. 7 into 8 into 8 into 5. So this becomes 7 into 5. So here, if your T1 and T2, they are different, so your attention matrix which is there, it might not be a square matrix. So here attention matrix will be softmax of score root decay of score. So again, it will be 7 into 5. And now you get the output. Output is equal to attention matrix into V, 7 into 5 into 7. K is V
It should
also.
be V transpose. V transpose.
No, it will not be V transpose. Sorry. For the row vector, when you consider, so V size is also 5 into 8.
So this DK is from encoder or decoder?
It is from the encoder.
Okay.
Okay. So this 7 into 5, please remember, okay, somebody had mentioned that it will be V transpose. It is not V transpose for the row vector. See, V size is also same as K, 5 into 8. Okay. Attention matrix size is 7 into 5.
Okay.
Output is 7 into 8. So I'm multiplying into 5 into 8. Okay. Okay. So it is attention matrix into V. So what has happened? I have gathered the information which has come from the encoder. I have enmeshed, I have done the key query and all that. And again, it passes through the linear layer WO. So I have got this. So again, here the parameters are how many? 4 into D model into D model. Is that okay?
Yeah.
Okay. Okay. And like with what we did in encoder, we passed now through the FFN. So FFN will have the bias also. So this 1 by 1 it passes. D model was 8 and we get again the output 5 into 7 into 8. Sorry. 7 into 8 we are passing and we are getting 7 into 8. Now this 7 into 8 which is there, now what it is? This is go, this is मैं, this is घर, जा रहा हूं. So when I pass go, so I got this not 7 into 8, I will get 1 into 8 this. So here I have to carry out a probability distribution over the entire walkup size. So I have to convert now into 7 into walkup size. Is that okay? Then only I'll come to know.
This is we are doing after FFN, right?
After FFN. So I have passed the decoder layer. This is the decoder layer. Decoder layer. This was MHMA. This is MHCA. And this is FFN. And here I get 7 into 8. I pass to the output layer.
Okay.
This is a linear layer. Okay. So now this output layer size which is there, it will be D model into walkup size. So that now I will get, for example, I take मैं, so it had only 8 dimensions, but now it will have 20 dimensions. Okay, so it will have these values which are there, 20 values. And now I do softmax on that. So softmax, what it will give me? It will give me probabilities. Okay, so if I know that ghar which is there, this is ghar, and its probability has come, for example, 0.4. And I know that after May ghar should come. So I will maximize this probability. So if you remember the lecture also, the GPT, when we were doing, this मैं घर जा रहा हूं, it has given the probabilities when we are doing the teacher forcing. So these probabilities have come. And what do? We maximize the probabilities of this and then do the back propagation. Is that okay? Is this part clear, okay? Or any question on this?
So what we are doing, like if we put go, it will generate some word. Suppose it is generating man. Okay, so it will give a distribution over the vocabulary.
Yes.
Okay, and which word of the vocabulary have the highest probability, we will take that particular word embedding and we'll give it as input in the next.
Yes. So that happens. What's your good name?
Ashutosh.
So Ashutosh, that what you have explained, it happens in auto regression mode. That whatever you feed, you get. Again, you feed, you get. So in the training mode, you know that
in
it's
teacher forcing.
that mesh should come.
No,
So
in a yeah. You're
okay.
right.
So in the training, what I will do, I know that my output should be मैं घर जा रहा हूँ. Okay. So this probability distributions which I've got in one go.
Yeah.
Okay. And now what I will do, for example, this may probability was less here. Here ghar was less. So what do? I maximize all these probabilities.
Yeah. Sure.
Okay. And what do? We are doing this teacher forcing because that's why I am feeding मैं घर जा रहा हूँ. After some time, what I will do, I'll remove them. Once the model runs the parameters, I'll remove them and then I do the auto regression.
Okay.
Okay. So that's how the GPT works. Any question on this? Anyone else? Okay. Because when I have covered this decoder and with this part, even the GPT is covered. How the GPT gets trained.
Sir, could you zoom into the input of the decoder?
Yes, please.
Like what happens when we feed these go, mag, and jara?
This we feed during the teacher enforcing.
No, I mean not like actual physical zoom, but like explanation wise zooming
Okay,
into the input.
okay.
Yes.
Sorry.
Like
So,
how professor says, we zoom into this part of the input.
okay. So I've explained this entire part decoder, so we can leave this.
Yes, you can leave that.
Okay. So what we did, we know that this is go, मैं घर जा रहा हूँ. Now, when I did this, at every step I pass go, it gave me probability distribution over vocabulary. Then to help the transformer or help this decoder to converge faster, to learn the parameters in a better way, I know that here math should be there. So next step I feed math. Third step I feed ghar.
This part, sir, I got. I mean that.
So okay.
I mean, at the end of that slide deck of introduction to transformers, they have that whole picture of the full architecture. And even from the decoder side, they have shown positional encoding and
Yes.
some sort of input.
So here also in the GPT, like GPT is a pure encoder model. So here also, what do? We do the embeddings. Embedding matrix is there, and there is a positional encoding is there. And unlike the pure transformer model, this positional encoding here, it is a learnable parameter.
So
Okay.
one question, sir. In GPT, we initialize positional encoding in the same way as we were doing, or different?
Yes, random.
Random, or sir, that sign cost?
No, it is not sign cost in GPT. It is not sign cost. In
Okay.
the original transformer paper, it was sign cost and it was never changing.
Mhm.
Here we are randomly initializing them, and then they are learnable parameters. So when we do the back propagation, you are updating this positional encoding also.
And again, one quick thing, like for BERT, we are also doing the same thing as GPT, is it?
Uh, about what, okay, this positional encoding and this embedding matrix?
Yeah, no, the positional encoding, I'm saying.
Positional encoding, I will check. I'll come back to you. I will
Oh.
not shoot it.
I guess in Bird you just have the segment
Yes.
encoding over there.
So the segment is different thing, but we also do some positional encoding there.
Okay.
Even the
So
position
we'll check that, okay, and we'll find out. So
Yeah.
let's okay. So what I was mentioning, there was a question now. So here, this part is understood by everybody. This one, that probability distributions have come, and we are maximizing this probability distributions. And how do we maximize? By taking the loss minus sum of minus
LN.
ln of y hat.
Right.
Okay. So if this concept is clear, then at least we know. So till now, I wanted to cover basically what is happening in an encoder, what is happening in the decoder. So if a question comes with a twist also, then we should be able to answer, okay, these things. What are the parameters? Okay, and like encoder in the decoder also, your, okay, this layer norm is happening.
So this embedding matrix is different, right, from the encoder?
This embedding matrix, this is also learnable. In the encoder also, the embedding matrix was learnable. So here also you do as per the your walkup size. So for example, you are doing from English to Hindi. Okay. I am going home today. English has go walkup size of around 30,000. Hindi, you say, for example, it is a 40,000. So here it will become different.
Yes.
Okay. So here this embedding matrix, okay, the concept remains the same.
So I'm guessing that when we are taking the max over probability, so we look up that argmax and whatever that token ID is
Okay.
from the vocabulary, that index, whatever that index is for the
Yeah.
maximum probability.
Yes.
Then we, at the next time step, we look up that embedding from this embedding matrix. And
Okay.
then, like, not training, while testing.
Yes, so in the inference mode, just I was
Yes.
writing na. So in the inference mode, you will take the word which has got the maximum probability. That might be 0.3 also, 0.2 also, but it is maximum. So you will take that word as the next input.
Yes. Okay.
Okay.
So we
Okay.
do that from the index of this one cross vocab size, right?
This will be from vocab size. So your vocab size is there, vocabulary is there. So it is indexed. So wherever it has come highest, okay, you will pick up that word.
Okay, thank
Is
you.
that okay? Okay, so I think the GPT also I have covered. Okay, so anybody wants to ask any question about GPT also in this?
Sir, like for a small summarization could be given for decoder, like number of parameters, how to
Okay,
calculate only in decoder layer.
okay,
Because for encoder we wrote, for
okay,
decoder means it will be
okay.
simple, I guess.
So decoder layer, decoder entire parameters, or we can say I will calculate for GPT. It's that okay? Okay.
Okay, yeah, sure.
Okay. So first, okay, we come to the embedding part, embedding layer. So embedding layer will have two for GPT. I'm covering. So this will be walkup size into D model and PE. PE size is how much? T into D model.
Yes.
Okay. So this we have covered embedding. Now we enter encoder layer, sorry, decoder layer. Decoder layer, the first part is NHMA. MA is 4 into D model into D model. Is
Yes,
that
correct.
okay? Then
Yes.
we enter MHCA. This is 4 into D model into D model.
Yes, same. Correct.
Then we come to FFN. So this will become D model into FFN plus FFN, and
With
then
bias, yeah.
FFN plus D model plus D model. Is that okay?
Yes. Yes, yes.
Then we come to output layer. Output layer size will be how much? D model into walkup size. Is that okay?
Sir,
Yeah.
that will be FFN cross T model plus T model, right?
Yes, yes, sorry. Okay. So these are the total number of parameters and plus your layer norms. Okay. So here how many layer norms will be there? In MHMA, one layer norm will be there, one MSCA layer norm will be there, and one FFN layer norm will be there. So in that it was 4 into D model, and here how much it will become? 6 into D model per layer.
Okay.
Is that
Okay.
okay?
Yes, yes. Got it. Yeah.
Okay. Okay. Can we take 2 minutes break? I'll have a glass of water.
Yes,
Sure,
sure.
sure.
Yeah, thank you. Okay, can we start?
Yes, yes.
Okay. So now can somebody tell me how the GPT is used for NLP task and for classification tasks? How can we use? We have covered, the major part of the GPT model.
So NLP means sentiment analysis, or what, sir?
Yeah, sentiment analysis, for example.
So for if it is the last token that we generate, no? After that, the output from the model can be bypassed to a network where it will give a binary output.
Okay.
Yeah, the last output. Yeah,
And similarly, we can do the classification also.
yeah, same.
So what we can do, we can put a linear layer here, and then we can train, because this token which is there, the last token, it is carrying all the information of all the previous tokens. Is that correct? So if I had, for example, a paragraph of 512 words, and this last token which is there, it has got all the information about those 512, like we used to do in the RNN. Is that correct?
Mhm.
And then we can apply a linear layer here. We change, okay, for example, this size, for example, it is 512 into 1024 D model, and I change it to, for example, and this was the 512, like tokens were there. So this is 1024. I change it to dimension 2, 0110. This is yes, and this is no. Similarly, positive or negative. So this can be trained, okay? And training also professor covered, okay? It can happen in two ways, that you train only this part, okay? The linear which is there, you freeze these parameters. Or second way is that you freeze only the half part of the parameters. So these are the two ways, okay, you do that. It is only for the conceptual part.
So in the second way, we are freezing only half part of the model.
Half part, okay. See, the training of this entire model is very, very costly.
Very costly, yeah.
Okay, so you would not like to fiddle, okay, with this, okay, for that. So shall we go ahead, okay, with the BERT, okay, if everything is clear?
Sir, one question I have in GPT.
Yes, please.
Like if we are giving that the input that is go token, after that मैं घर जा रहा हूँ, right?
Yeah.
And after that will generate one by one output. Suppose there is one word in the vocabulary that we are generating, like the decoder is generating after pre-training, and like we are giving that output in the next sequence, right? Suppose we are giving go and it is giving some junk like some different output like
Yes.
hai. It
Okay.
should generate my, but it is generating hai. Then then the in next sequence hai will be given as input, and the embedding of hai shouldn't be updated in the updated, but in that case it will get updated.
See, the same output which you have got. So there are two phases. One is the pre-training, and second is the fine-tuning.
I'm not talking about the fine tuning. Yeah.
Okay, so we come to the pre-training also. So pre-training also has got two parts. We start with the teacher forcing,
Okay, teacher forcing, and yeah, this.
and then we come to auto regression. Okay, and similarly when you do fine tuning, then also you tune, okay, with the labels now, with the correct data.
So we are in auto regression phase then.
So auto regression, it means already you have done the teacher forcing.
Yeah.
Okay, so it means there is a high probability that it will generate now only.
But suppose it is generating some junk. Suppose.
So then the same output which has come, so it had dimension, for example, 1 into, so for example, 1 into 20 walk-up size.
Mhm.
When it comes, okay, it passes through the embedding matrix, okay, it becomes 1 into 8.
Mhm.
And then you pass, okay, that. So whatever the output is coming, you are passing the same as the input.
Mhm.
And again it will generate. Again you just add, so some gibberish will come, not
Yeah.
any meaningful sentence.
But it could update that embedding. Like there was a question in week 3. That's why I'm asking this.
Week 3, what is the question?
Week
Can we-
3.
That
Week
case,
3,
matrices were shared.
question 4. Yeah.
Okay, just hold on. I will open that also. Week 3.
Question 4.
Choose the correct statement. All the parameters of the GPT model are randomly initialized. Question 4, sorry. Assume that we have a large corpus of text. The vocabulary constructed from the text contains 10,000 words. Okay, this is a different thing, okay? The question which you have asked is different. It says that your sentence is go, मैं घर जा रहा हूं. Okay? And this does not have a word, okay, for example, sadak.
Yeah.
Okay. Now, when you do the final output, you are doing the entire probability distribution in which sadak is also there.
Right.
So this sadak might not be there in this sentence, but its weight might get updated. If you remember in the deep learning, in the output, okay, we had the same conceptual questions.
Yeah.
Are you getting my point or not?
No,
This,
like yeah, continue.
so this weights which are there for this sadak which is there,
Mhm.
the sadak might not be there, but when you are updating this probability distribution, you are maximizing.
Right.
You're maximizing for everything. So sadak is somewhere here, okay, also in this.
Okay.
So,
Mhm.
so it might not be here in the input, but your back propagation when it does for everything. It will not change only for may.
Mhm.
Okay, so WQWV and this word embeddings which are there, your this embedding matrix which is there, this sadak also might get updated.
So, like while we are generating the output, the distribution over the vocabulary, we are
Yeah.
just passing through the neurons, number of neurons that's equal to number of vocabulary, right?
Hmm. Hmm.
Vocab size. So, I'm not getting how it is getting the embedding of the word sadak to be updated on first.
Okay. See, okay, I'll give you the example of okay, deep learning. Here it was there. So this matrix is there, this matrix is there, this matrix is there, and you have passed okay, some input, and you get some output, and it is not correct, for example. So do you think it will only update for this only? So these matrices which are there, they all are getting updated, na? We used
Right.
to do W is equal to W minus delta W into that again new.
Yeah,
So that
everything that's been connected. Yeah.
yeah, so your entire W is getting updated. Okay, there was a question na, that okay, it was wrong, and here we were having 0 0, and there was a question whether okay, this W3 will get updated or not.
Yeah, it will get
Okay,
updated.
so this will get updated. Similarly, this sadak might not be here, but when you are doing the back propagation, when it is coming, so this your embedding matrix which is there, and wherever that sadak point is there, it might get updated. You cannot say that it will not be updated. It may or it may not be updated. That is a correct understanding.
No, but my question is still that like if we are not passing the embedding, if the network doesn't know the embedding.
No, no. Embedding, you are not passing, but it is there, na?
Mhm.
This embedding matrix which is there, your how many words you are passing? You are just passing 7 words.
Yeah.
Okay, but your this word embedding which is there, embedding matrix is there, it is of 20 size.
Right.
Okay, demodel into 20 size. So this is having for all the 20 words in your embedding.
Right.
So it is having for sadak also.
Mhm.
It is not having only for this 7. And when this back propagation, okay, loss, okay, when it comes, it not only does for may, it might do for sadak also. That is a point.
Okay.
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 Okay. Any other question?
No, sir. Thanks.
So one more similar conceptual question in
Yeah.
GA2 question 4.
GA2 question 4. Okay.
They've given the answer as -1. I just want to know the correct reason for why -1.
GA2 question 4. Okay, just let me check. Yeah. I had you saw my this solution I had shared on the
Yes,
WhatsApp.
yes. I also came up to
Okay, okay,
0.1.
okay. So this is the same concept. Okay, I had also written. If you see my answer, I had also given the wrong answer. And when this I saw retrospectively, immediately I came to know why it was wrong. And the same reason which I've said. The same reason. See, it is saying ki some word is there. For example, I am going home today. Okay. Now the distribution which I found, will it do only on these 5 words,
No,
or
for
it will
the
do over entire vocab?
yes.
So we should not do 1 minus okay, probability of this, and this.
Yes.
Okay, so that was the case.
Thank you.
Okay.
Sir, can you just solve the first 3 questions? Then we'll have an idea that. I mean, you
PYQ,
did it. Yeah, no, that GA 2 1 2 3.
GA 1 2 3. Okay. Okay.
GA2.
So can we try out again, all of us again, GA3?
No, GA2 ka 1 and 2 and 3.
Okay.
The first 3 questions.
Okay. Have you tried again? Did you get the correct answer?
I was trying actually, but no, I didn't get the correct answer.
Okay. Okay. So assume the model has 2 layers. So I will just copy it here. I remember I calculated and at the first go I could find the correct ticket. So we can solve it. No problem. I will solve it again. Wherever I go wrong, please, okay? Somebody can correct me. Okay? That's okay? Our agreement? So,
Yes, sir.
okay. So we pass the sample from the source language. I enjoyed the movie transformer to the encoder and its transition is this to the decoder. All the learnable parameters are randomly initialized. The model uses the teacher forcing approach throughout the training process. Total number of parameters excluding the embedding layer and the output layer. Okay, very nice. So this will contain only, so this is a decoder.
Yes.
No, it's both the
Yeah,
encoder and
it's
decoder.
an encoder, I guess.
Okay, so encoder will have attention layer. Attention layer will, has it they given 2 heads, only number of layers, number
4
of
heads.
heads. Okay, they don't matter. So D model is how much? 64. So 4 into 64 into 64. Now we come to FFN. FFN they have given 256. This will become 64 into 256 plus 256. Somebody please calculate this, okay, just to help me out. And users layer norm and
They
response.
mentioned no bias is added in the question.
Where? Okay,
Moreover, no bias was added.
okay, okay. And layer norm will become 4 into 64. You find this, multiply by 2. Is this okay? Encoder part okay? Decoder MHMA plus MHCA will become 8 into 64 into 64. FFN again will become 64 into 256 plus 256 into 64. Layer norm will become 6 into 64 multiplied by 2. Can somebody do this calculation?
Yes.
Yeah.
So for encoder, I'm getting 49408.
Okay, and in the decoder we have forgotten one thing, walkup size. But they are saying number of the parameter in the output layer. Output layer we don't have to consider, no?
Yeah.
Yeah, so this should be the answer. So this will become
Okay.
Sir, when I asked about the scaling factor DK,
yes.
so in MHCA, it's from encoder, but what about MHMA?
MHMA, so we are using everything from the input
From the decoder
from
side, right?
yes, in the decoder, everything
So,
is coming from the input. No? So it will become D model.
no,
D,
that scaling factor, square root of DK.
so scale factor, okay, this root of dk which is there, it depends on the size of your k.
Yes.
Okay. So if it is 64 into 64, then it becomes 64. If it is number of heads, it can become, for example, 8. So this will become 8.
Okay.
Okay.
Thank you.
Has somebody done this calculation? Or shall I open my this? I've got the solution of
Yes,
this.
sir.
Huh?
Yes, sir, it's done. For
Yeah.
encoder, I'm getting 98816
Yeah, same.
98.
816.
Okay.
For decoder, it's 132224.
132224. 231140. And answer is how much? 23656.
The encoder will be 98304.
Huh? Just hold on, just hold on. I will calculate. I will just open my calculation. I've done this question.
Linear layer speed.
WO to we have joined, na?
Yes.
WO to we have considered. It was week 3.
Week 2.
Week 2, week 2, week 2. Notes here. This is the question, na? So see, this is the encoder MHA 64 into 64 into 4, 16384. Normalization 64 plus 64, 128. That is correct. FFN 64 into 256 plus 256 into 64, 32768. Normalization 64 plus 64, 128. So this is correct. 98816 who had given me this answer. This was correct. And this multi had attention 4 into 64 into 64, 64 plus 64, 4 into 64 plus 64, 64 plus 64, 65920 it comes, and there are 2 layers. So it is the same. Okay, we have done the same. You do this calculation, you will get the correct answer. You have not omitted anything.
Right. Sure.
Can somebody do this calculation? It is correct.
Yeah, let me do here.
Yes. Let me do also.
Yes, it's correct. Yeah.
Yeah, it's correct.
It's correct?
Yeah, yes.
Yeah, yeah.
Yes.
Correct. Yeah.
Okay. Okay, if you know the basic concept, okay, then you will not go wrong.
Yes.
Now, if what would have happened if the embedding layer was there and output layer, then you would have added 2 into walkup size into D model in encoder, and same in the for the decoder also. So it would have become 4 into walkup size into D model. Is that okay?
Yeah.
So output layer will be 1 only, right? Totally.
Output layer will be 1 only.
Okay.
Okay. Another question. How many parameters does the output layer have? How many बताओ output layer का
So
size
even
क्या होता
then,
है?
it won't be 2 into vocab size because vocab size are different for both the
Yes,
encoder
yes.
and decoder.
If they have given it. So depending on that, parameters कितना होगा output layer का? Walkup size into D model. It is straight away. Is that okay?
Yes, sir.
Yes. Okay. Yeah.
है ना?
Yes. Yes.
So this is okay. Parameters is equal to output layer is
Yeah.
nothing but walkup size into D model. You can multiply that, you will get the answer.
Yeah.
How many parameters do the embedding layers have? Embedding layer का कितना होगा बताओ?
Vocab size.
हाँ, इसमें अलग अलग दे रखा है ना, सोर्स वोकैबुलरी का अलग दे रखा है.
So source vocabulary into what?
हाँ, बस तो वही है, नथिंग एल्स. वहां पर क्या आप इसको डी मॉडल टारगेट से करेंगे आउटपुट को, और इसको इससे करेंगे. सो 1000 into 64 64,000 हो जाएगा, और इसका 1500 into 64 जो आंसर है यहाँ पर 96,000. इज दैट ओके?
Yeah. Fine. Yeah.
या ओके.
So, basically, fifth question you have, like if you scroll down,
Fifth
Yeah.
question. Yeah.
it's called, yeah.
Yeah.
Well, scroll up. Then the sixth question. Yeah.
Oh,
Fifth question. Yeah, this one. How do you solve for the gradient vectors? Like, how do you proceed with this?
You have to do the calculation for this.
It's a big calculation.
Yeah. For this, okay, you'll have to multiply this, okay, or you can write a Python code and you can find out that.
Got it.
So can we revise previous year's papers?
Which one? PYQ.
Can we start with PYQ?
Yeah. So before that, I wanted to cover again the decoder also. Sorry, BERT also.
Okay, sure.
So
Okay, fine.
see, the question might come in different forms, but what I feel, if the concepts are clear, we'll be able to answer, and it's far easier to solve the questions if the concepts are clear. So we just take 5 minutes for BERT. Okay, BERT is also easy.
Yeah, sir. Sure.
Okay. So in the BERT, okay, BERT is first of all, it is a pure encoder model. Second, it is bidirectional, so it does not have any masking. Okay. Now tell me, if the GPT comes and they tell you to find parameters, so what you will have to do? We will not use MHCA. Is that okay?
Yeah.
Because there is no encoder in GPT. Okay. So in BERT case, everything remains same. We pass the input, okay, but when we pass the input, what do we do? 15% of the words which are there, we mask them. So for example, it was I am going home today evening. So I will mask this word. And when we pass this entire thing, the process remains same. It will give me the probability distributions, probability distribution. And unlike GPT, we only are concerned about this one. So what do? We maximize the probability of the word which should have been here. So we will maximize the probability of going. If there were two words, for example, today, then this was masked, then we do maximizing of the probability of this also. And how do we do maximizing? 1 by n summation of minus ln of y hat. Is that okay?
So in the GA, sir, the answer is that they hadn't considered that 1 by m part. So
Okay, so in the discourse, okay, I had also written okay, 1.7 is the answer, the 3.45. So I had written okay, so they have given me the marks okay, for that. I'll just show you. I raised okay. This was week 3, week 4, no? See, 1.725. So they have given both answers. Both answers are
is true. Okay.
Okay, you can do both again. You can if you remove m also, it does not make any difference.
Okay.
But in the slide they have mentioned, that's why I had applied that formula. Okay.
And for this architecture also, if the word is not frequent, then there is also a chance that their embedding will get updated, just like GPT, right?
In this you are yes, so you are doing going minimize when you'll do, so entire vocabulary is there in this. Okay, so there might a chance that here the embedding matrix which is there, this word might not be there here in this, but it might get updated.
Okay.
Okay. Now, shall we cover some basics of decoding strategies? So, decoding strategies we have been taught, there are two ones. One is deterministic and the second is stochastic. So, in deterministic, we had exhaustive search, then we had greedy search, and then we had beam search. Any question on these? Both on all three? Anyone? Stochastic is top K sampling, and second is top P sampling. If any question is there, I will explain this. And this is for both again, all the LLMs. It is not particular only for GPT or for anything. Any question on this? Anybody wants to know anything about this? Deterministic, stochastic, how do we do that? Okay.
So you can explain those minus ones in GA for assignment. They're about the decoding strategies and their
Yes,
peculiar.
yes.
Okay.
So I'll do that. Okay. So there is a lot of confusion about those questions. So I will straight away go to this only. So see, this is the first question. Is this visible to everyone? And everybody see?
Yes, sir.
Okay. So this, consider a vocabulary V. This is a vocab. Assume that we have a pre-trained GPT model for the text generation, and the first input token to the model is always the special token start. The prediction probabilities outputted by the model are given below. So see, this is start, and start has given these probabilities, and we can map all these vocab words to the probabilities. Is that okay?
Yes, sir.
So this is timestamp 1. So what happens? The zeroth row of the matrix is the output probability distribution by the model given by the special start token as input. Following the greedy search decoding strategy, the subsequent rows give the conditional probability distribution. If you think the given information is insufficient, then okay. So we go to question number 1. What is the probability of the predicted word astronomy given the word start? So we are at this start. And where is astronomy? Astronomy is 0.41. So answer will be 0.41. And now as it is a greedy search, so in the second, what it will feed again now? Astronomy.
Yes, sir.
Okay, so now astronomy. So for astronomy, what has come? 0.41 43. So this has come. So next word will become is that okay? Now here 0.29. So next word will become a. Now in this 0.48. So this will become character. And in character is 0.29. This is building. So by greedy, what is the sentence which we have got? Astronomy is a character building, and in building, what is the highest is 0.23 experience. Okay, I think the next question is that only, and we have to find that what is the probability of this entire. What is the probability of the sequence? This. In this also, they have given both answers because the question is ambiguous slightly. Because after this, an AND token should have also come. Okay, after experience, here it should have started with experience. And when you make the probabilities, then this AND which is there, its probability should have come highest. For example, 0.4 and rest all normal. But they have considered both. Now, what is the probability of the sequence? So we know the probability of this sequence will be P of astronomy. I say this is A, this is small I, this is small a, this is big C, B, E. Is this okay? So this will be P of A divided upon start. into P of A and I, sorry, I over A and start into P of A, A, S, and I into P of C, A, S, I, A into P of B upon A, S, I, A, C into P of experience upon A, S, I, A, B upon P of and upon all this A, S, I, A, B, E. Is this understood? Okay, this part by everyone?
Yes.
Okay. So now you just find okay, these probabilities and you multiply them. In the question, they had not given this part. That's why if you answer -1 also, they have given the correct answer. Okay. Otherwise, you find this probability. So this probability you can find from the first 0.41 and you keep on multiplying all these probabilities which are there because it is sequential and it is in the correct order. And that's why the answer has come 0.0016. Now we go to the next question. What is the probability astronomy is a natural science? Now for this, astronomy is A, it has come in this. If you see, astronomy is A has come. But for natural, here the natural should have the highest okay? Somebody had asked me that question. Can you tell me your name, please?
Herman, no, natural is not the
Okay.
highest.
Okay. So when the natural is not there, so there is we cannot find the probability for that. Is that okay?
Yeah.
Okay.
Yes.
So that's why the answer for this natural is this did not come after A in the greedy one. So that's why the answer is -1.
No, can it be zero, the answer? Because the search wouldn't give natural, so the probability would be zero because it will never generate this.
No. Uh, you are right. Okay, if you take the greedy algorithm, it will be zero. So we can contest that on discourse. Is that okay?
Uh, so you said -1 with what?
Because they
Do,
have mentioned here. They have mentioned if you think the given information is insufficient for any sub questions, then enter -1 as your answer. So this
but
information
but what do we lack here?
we lack here that I don't know where that okay, you are right okay, that if the greedy is there okay, then answer should have been zero. You're right. But I don't know where this okay, but I don't know where this natural is there. So for greedy, I agree with you, it is zero. However, if it would have been exhaustive search or it would have been beam search, then I don't have any complete information. So this again,
No, the probability of natural is still there.
but natural is there. See, greedy, what happens? Greedy, what it does? It takes one word, it gets this word. Now, whichever highest probability word is there, it takes the next input. Then, whatever the highest probability is there, it takes next one. So, this natural which is there,
So natural is not a
yes. So, natural is lesser.
right?
So, it will never take natural. Are you getting my
Okay.
No,
point?
I'm saying the what we lack here is the probability of science given astronomy is a natural, because we already have the probability of natural given astronomy is a.
No, no, no. See, greedy, how does it work? Okay? Greedy
No,
work.
I got it. I got the
Yeah,
one
yeah.
intuition for
So
greedy.
I agree with the this ki zero. If you write answer zero also for a greedy algorithm, okay, it will be right. Okay. Greedy
But
step.
even if it's, let's say it's exhaustive, so uh, I guess the reason for writing -1 would be
See,
that we don't.
okay. So I say for okay. So I will say if it is an exhaustive one, you come here. Astronomy is A, and then you will take natural. Okay. Where is
Yes, a
natural?
natural, I guess it's 0.07
Okay.
here given.
But now you cannot take natural now, because for the natural, the next word which is there, the natural distribution is not there. See, these probabilities which are there, you have to understand, these probabilities are sequential. That this much has happened, then what is the probability of this?
Yes, so that is what I'm saying. So we we write -1 not because the probability of natural is not given, but because the probability of science given natural is not given.
Yes, yes.
Yeah. So
Okay. And A, after A, natural has not got the maximum probability for the greedy algorithm, for the greedy strategy.
What I thought is up to natural we are getting, but science we are not getting.
No,
yes.
no. Yes, yes. Okay. So A, which is there, you have got natural. It is natural where? So you have got natural. But now in the greedy, you will not pick up a natural now.
Yeah, that is character
You
given.
you will always pick up the highest one. Okay. For the exhaustive, yes, I agree with you. You would have selected 0.07. But now for natural, it is not good. Okay. Can we go ahead again to the
Yes.
next question? Yeah.
Yes.
Okay. Okay. This is a question. So a lot of discussion has taken place. So I can answer this question. So next question is this. If we use top case sampling with k is equal to 3, what is the probability of the predicted word equal to astronomy given the start? So you see here, you have done the start. So this is the first part. Okay. And now after the start, you have got the probability distribution. So k is equal to 3. So you'll pick up what again? You will pick up top 3. This you will pick up 0.41 astronomy, 0.14 character, 0.09 is for is. And what do we do for prediction? Again, they are asking the probability of prediction. So what do we do? We do the normalization of this. Are you getting my point? Okay, we do the normalization in case sampling.
Yes.
Yes.
So we will do 0.41 plus 0.14 plus 0.09. And for astronomy, it will become 0.41 divided by this. This comes 0.64. So correct answer for this question is 0.64. -1 is not the correct answer. Probability for astronomy to become the predicted word, and then only it will go to the next one. To go to the next one, then we follow that random number we generate and we find out where it is coming. But for the probability for this astronomy to be selected will be this probability
Yes, sir.
in case sampling. Okay, so 0.64 again, it has been answered in the discourse also that 0.64 is the correct answer.
Okay, sir.
Sir, if it is top P sampling,
Huh? So in
top P.
top P sampling, then okay, they will always give you the P value. So they will give you P is equal to, for example, 0.9.
Okay,
So
the
you will,
whichever
okay, so
probabilities are, it's like a threshold.
it's like a threshold. So you will take all till the time you reach 0.9.
Okay. Okay,
Okay.
got it. Yes, yes.
Okay. So that is the only difference between K sampling and the top P sampling. In top K sampling, we always take only those number of Ks. In top P, it is random. It depends on the probability. So sometimes you might take only 3, sometimes you might take even 7. Okay, that is the difference.
Yeah, got it.
So somewhere in the slides they mentioned we divide by the length of the sequence so that longer sequences don't get
Yes. So
shrunken
that is
down too much.
okay. So that happens for what? Okay, beam search. It happens for beam search because when you are doing beam search, so here you have got 1, 2, 3, and 4. So this like a sequence length which is there, it is 4, and you have got some probability. Here you have got some length of 2 only, and you get some probability. So what do you do? This log of this probability which is there, you divide by the sequence length to compare which one is higher. Otherwise, the one which is has got more sequence length, always its probability is always less than 1. So when you multiply the decimals, it will always keep on decreasing. So that is the reason you divide it by the sequence length.
There is a discourse thread that if we divide by the sequence length, then the probability gets smaller further.
So he has answered, okay, that you divide by the log of this, okay, by the sequence length. You take the log of probability, divide by sequence length. I will just open that. Okay. I was going through that discourse.
I didn't get it actually. I know that he answered.
Okay, this was for 0.64 and gradient G2. He has answered somewhere. I will like post it on WhatsApp. Okay, I'll find the answer for that and I'll post on WhatsApp.
Sure, thank you.
Then this one is this already we have seen that 3.4 wala. So there's no BERT model. Okay, feature extractor and all that. Okay. So in this answer for this question is, has everybody done this question? Question number 6 of GA4. That can we use any token, like in the BERT, they say that CLS, which is a special token. You have seen a BERT, we pass, so there is a token CLS. And here is we are passing this information. And this CLS which is there, its embeddings which are there, we use them as a feature extractor. So they ask that we can only take the representation of CLS, or we can also use the representation of separator also. There is a separator, or we can take representation of any word, which is there. So answer for that is that CLS is a special token which is optimized to gather all the information of all the words. Whereas if you take any word, then this word which is there, it is getting optimized for itself only. So that's why the reason is this. It is a theoretical basically from the paper. Shall we do the PYQ now with that?
Sir, also the position of CLS, can we alter the position of the CLS?
Really, I don't know. I will not be able to answer. Whatever has been covered in the lecture is that the starting is the CLS.
Yeah.
Okay. So it depends on the implementation where you want to do that. So this is the PYQ. Has anybody tried to solve them? Or we do that? So it's a same easy question. Consider a vocabulary V is equal to ATCG, and the corresponding embedding matrix is E. So this is the E. For example, the 0th row of E is the embedding for 0th token of V. So for A is this, T is this, C is this, and G is this. The following sequence X is equal to GCCTAG is to be processed by the encoder layer of the transformer architecture by appropriately adding the positional information using the following encoding scheme. So here they have changed the formula. Instead of 10,000, they've used 10. Okay. Assume that index for the position starts from 0. Add positional information to all the tokens in the sequence. Let the resultant sequence be denoted by H is equal to E of X plus P. H will be used in the subsequent questions. Please write it down. Here EX denotes the embedding matrix for each token in X. So how we have to go about it? So this is your input GCCTAG. G embedding is 1 1. So we write 1 1. C we know it is 1 minus 1. C again 1 minus 1. T is 0 1. A is 1 0. And G is again 1 1. And now we find the positional encoding for them. So this is the position, and like I had covered earlier, this becomes your I. So this is 1 1. So for this both, I will remain 0 0. Okay, I had covered here if you remember. So straight away when you fit this formula, So PE for G, for example, it will become sine of 0 because position is 0. So sine 0 and cos 0. So this will become 0 and 1. When you use for P of C, C is at position 1. So it will become sine of 1, 10 to power 0 because I remains 0 for all. 0 by 2. So it becomes sine 1 cos 1. And we keep on writing. Similarly, P of again C, position C, sine 2 and cos 2. And this how we calculate the H value. You add this. Now they have asked the question for the P5. So P5 will be where? It will be for this G. So for G, P of 5 is the position minus 0.95, which is sine of 5. And this is cos of 5. And when you add, then you get the required answer 0.67. But they have also asked us that please write down the values of this H. So whatever this H which is there, you add the embedding and the positional encoding to get H. So this is the H which you get. Is that okay till now? Any doubt in this?
Yeah, got it. No doubt.
Okay. We go to next part of the question. What is the sum of the elements in the third token? What is the sum of the elements in the third token? So third token we come here. This is H0, H1, H2, H3. So this is H3, 0.14, 0.02. So it becomes 0.16 answer. Now they have written the bottommost encoder layer of the transformer contains, these are the values of WQ, WK and WV and WO. Given that the embeddings are row vectors, so they have especially mentioned these are the row vectors. So we have to use the same notations which we just now covered during the revision. That Q will be equal to X into WQ. Okay. And output will be equal to score attention matrix into V. Compute the attention score to produce the new representation for the token T at the third position in the sequence X. So see, this is H, and they have also asked that write down the unnormalized attention. So don't use this root decay. So little bit of mathematics is there, but very easy. You do find Q, you find K, and then you find scores. Scores is nothing but Q into K into transpose. When you multiply this, so for T, so these are the scores which you get. So this is the H. These are the various tokens which are there. We have to find for T and with respect to A. So A has come here. So this is 0.14. You will keep on multiplying that and you will get the answer for that. So answer comes minus 0.056. Simple maths is there. Only steps, okay, we know what are the steps. Any doubt in this question? Anyone?
No doubt.
Now the next one, the bottommost encoder layer of the transformer contains this. Again, they have given the same WQ, WK, WV, WO. Compute the attention score to produce the new representation for the token T at the 30th. I think same. We have already found. Which token in the sequence was given the highest score? Okay, so when we do for T, T will give, so this is the T. So we have got for all. So they have asked which one is the highest. So when you do the multiply, you will find this 0.42 is the highest for G. Consider the following configuration for the vanilla transformer architecture with one encoder and one decoder layer. Source and target workup size is 100. Maximum sequence length is 32. Length of context window T for both encoder and decoder is 32. This is T. Sequence length will become D model. Number of heads is equal to 2. DFF is 4 into D model. DQ is equal to DK is equal to DV. D model by this is something and A. Something number of heads, sorry. Suppose the number of learnable parameters in the source input embedding layer is 1600. How many parameters are there in the positional embedding layer of the source language? So always remember PE, what is the dimension of PE? It is always T into D model. For example, this was I am going home. So इसका जो dimension है positional encoding का, it is same T into D.
Yes,
sir.
Okay. And embedding layer का size क्या होता है? D model into workup size. This we had covered during the revision.
Yes.
So from here we can find D model. D model is equal to embedding layer size divided by the workup size.
Yes, sir.
Okay. So they have given learnable parameters, and this is 1600. So this is 1600 divided by walkup size. So you have got D model. Once you get, so every token is represented by 16 variables. Number of parameters in P is n into D model. N is the sequence length. Therefore, number of parameters P is 32 into 16. So that's how the answer is come. Basic mathematics, class 8. Any question in this? Anyone? Just for you to remember, okay? Just concepts, okay? Simple. How many parameters are there in the multi-head attention layer of the encoder? Exclude the parameters in the WO matrix used for the linear transformation. So directly we can write there are two heads. So we have calculated this is the 16 is the D model divided by number of heads, it becomes 8. So this will become input is 32 into 16. This will give output 32 into 8. This will give 32 into 8. We get 32 into 16. And these will become the number of parameters. Okay, and they have exclude the WO. So WO is not included, sorry. And if you find the same, it becomes 3 into D model into D model. Straight away you can use this formula also without going so much in detail. So this will come 3 into 64 into 6, 3 into 16 into 16. So you'll get the answer. Okay. This I drew just to explain in a better way. Now this is the question. Let RE belongs to RT1 into D model. This is the topmost encoder layer of the encoder. So this is the output from the encoder T1 into D model. ZD belongs to RT2 into D model, be the output of multi-head masked attention layer. So this is the MHMA output. What will be the size of the attention matrix in the multi-head cross attention layer of the same? So this is very easy. Can we do it again very quickly? Can somebody tell me how to solve this?
Yes, sir. Q will be coming from decoder, and that will be T2 plus T1.
Okay. So see, again, just to revise the concepts, this is the MHMA. This is giving output of T2 into D model. This is R. This is T1 into D model. Okay. And this is given dq is equal to dv is equal to dk is equal to d if required. This is same. So your wq, wk and wv size is what again? D into d. Is that okay?
Yeah.
Okay. So here, what will be the size? Okay, when you multiply this by d into d, you will get t2 into d.
Yes.
Here, when you multiply by d into d, what you get? t1 into d. Okay. And this is your k. This is your q. So your score will become q into
K transpose.
K transpose. So this will become T2 into D into D into T1. So this will become T2 into T1.
Yes.
And attention matrix का जो size होता है क्या होता है? Same होता है score का.
Yep.
So answer will be T2 into T1. That's okay.
Yes.
Okay. So see, all the questions are on concepts only. Just you have to apply the concept and you will straight away will get the answer. Don't go into the complexities of that. Now, suppose we run the pre-trained GPT model in an auto-regressive fashion for generating a text sequence. Then the statement that we do not need to add the positional embedding to the predicted tokens at every time step. This is true or false?
True.
Positional encoding. See, the decoder has started. Just think, kya? The decoder has started. It does not know how many words are there in the future. So he has started generating. He passed this. He passed this. But at least he should know the position of these words at least. When he's going. Are you with me? Anyone?
Yes.
Yes, sir.
Okay, so Madhi, when you are going forward, at least he should have the positional information at least about these that these there were three words okay, before me, and now
Mhm.
there is a fourth. So when it says we do not need, it means okay we need okay. It's a
False.
false. Okay, conceptually it is false. However, in the modern architectures, what do? They pass okay positional encoding in the starting only. How do they do? I'm not sure. But as per the present understanding of the course till now, it is false. Okay. Suppose we have a data set for machine translation task with thousands of samples. Suppose a team considers training the transform model. That model could be trained in two approaches: auto-regressive, teacher forcing. So this is straight away we have covered here. You can easily find the approach A helps the model to converge faster than approach B. It is false. Autoregressive does not converge. Approach B helps the model converge. Yes, that is true. One can start the training with approach B first and then switch to approach A after some training steps. True. It is covered in the lectures also. And for this A, it is false. Okay, this question, a team trained a language model using the GPT architecture using a large corpus of text. The model configurations are given below. Walkup size 30,000, D model 512, context window is 1024, DFF 4 into D model, DQDK 64. They trained the model for millions of steps and stopped the training after the loss had decreased significantly. Then they use the model to generate the text by giving the special token BOS, beginning of sentence, as an input to the model. Select the length of the text sequence that the model could generate. So see, this model will keep on generating. It can generate any number. Any number one comes, it will keep on generating till the time your end comes, or you put a condition that maximum length generate I want only, for example, 1000 only. I want 2000 only. Otherwise, it will keep on generating, and it has got a sliding concept. So what it does, 1024 is the context size. So it process 1024 does and has not come, so it goes to the next. So it takes next 1024 and has not come, next 1024 and has not come, next 1024. So it can generate any number of words again. Is that okay? Clear?
Okay.
Okay. I'll share this document with all of you. I've given some explanations also on this. This sliding concept I got from GPT, and Dr. Ganesh had covered this how it happens in the WhatsApp group. Okay, then the next question is, I think this is the last question. Consider a GPT model used for CLM. We feed the input sentence. This is a cool idea to the model by appending special starting BOS and ending EOS tokens. That is BOS, this is a cool idea, EOS, we have passed. Assume the context length of the model is 7. The attention matrix computed in one of the attention layers is given below. So what will be the size of your attention matrix? It will be 7 into 7. T is 7.
Yes.
Okay. And this is the your attention matrices. So attention score matrix given in table 1 is appropriate for causal language model task. Is it true? This is true. What is the basic aim objective of finding the attention matrix? In GPT we are using that for decoder.
Yeah. So this is after applying the mask thing, right?
Yes, yes. So this see, so for this question,
Hmm.
we see this and just seeing this, we say yes, it is true. Okay.
Mhm. Yeah.
And the second question is assume the time step starts from t is equal to 0 ends at t is equal to 6. Suppose the model is at time step t is equal to 4. What is the attention value assigned for the word is? So see, we come to time step t is equal to 4. So we come to 4, we see the attention for is, it is 0 in this. Okay, so answer is 0. So this can be asked again in some other format also. Just see this question and you will get the idea how to hack it. Any question in this on this?
No, sir.
Okay, so this is all like the PYQ questions. So all on concepts, basic mathematics, nothing complex. So I'm sure okay, we will be able to hack it. Any other question anybody wants to discuss?
Sir, if you could share the recording of this meet, it would be really helpful.
Yes, yes, definitely. I'll share again this recording.
And the document also, if you could.
Yes, yes. I'll share on the WhatsApp.
Actually, I'm not in the WhatsApp group, so can you send the link of the group?
Link I don't have, otherwise I'll post on the G Space also.
Okay, okay.
Okay.
Yeah.
Chalo, thank you. Thank you for joining. Have
Thank
a nice
you.
day. All the
Yes.
very best for your quiz. Thank you. Bye bye.
Thank you, sir.
Sir,
Thank you.
Yes, yes.
sir, can I ask a question related to game theory?
Ha, game theory. Yes, yes. Aditya, please.
So in the GA4, should I present my screen or you can take the notes?
No, I'll open it. GA4, na?
Yeah.
Okay, which question?
It's one of the last ones. Let me check.
Which one, batao?
Mm. One second. Sir.
Yes, yes. How this number of sub game this has AFT, BC. Okay. Revise later on this. Correct answer was AFT.
So rollback equilibrium and SPNE is both are same, right?
SPNE and rollback, they both are different. Okay? So this question okay, which was there today. Hold on. See if, for example, if there is a game, this is one, and he takes some
Okay.
step, he goes here. Number
Okay.
two, he takes some step here, and then one takes a step here. So in this, the number of games which are there, you see, first sub game,
Yeah.
second sub game, and
Yes.
third sub game. So
Correct.
in this kind of sub game, your you can either apply rollback
Okay.
or you can do the sub game also to find the Nash equilibrium. Because here 1, 2 and 1 they know all the information what the player has done.
Correct.
Okay.
Yeah.
Now, so there are two ways of find the Nash equilibrium, either by the
Best response.
back, no, no, not okay, this in this type,
Backward.
backward induction, number
Okay.
one, or you do the sub game equilibrium.
SPNE. Yeah.
Okay. Now, when a game is like that, that when you don't know, so this one has taken some action.
Okay.
Now this two has taken action, some action, but now one does not know what two has done. So we denote by this dotted line.
Yeah, correct.
Okay, and when you do this, so one can take action here also, and he can take action here also.
Yeah.
Okay, so in this case, okay, your rollback which is there, this is was a perfect game. Okay, all the sub games. So you could do rollback and you could find the Nash equilibrium.
Mm-hmm. Mm.
Now here, what you have to do first, you have to use the normal form of the game. Okay,
Okay.
I'll just give you an example. This is, for example, AB. This is
Okay.
CD, and now the one has got the option to play, for example, EF. So one is EF here, one is EF here, and
Okay.
his, for example, payoffs. Okay, I will just give you an example. This is two
Okay.
two. This is 3 1 0 0 0 0. The same example I'm taking from that paper.
Okay.
Okay. Now, what are the strategies for the normal form here? What are the strategies with one? One can play AE, AF,
Yes. Yes.
BE, and BF.
Yeah,
Two can play CD. Now,
correct.
using this information, you find the NEs first. Okay. So
Mm-hmm.
this is 2, this is CD, this is 1, AE, AF, BE, and BF. So when you write
Based
this,
on this payoffs, we will find Nash equilibrium. Yeah.
but that you will use that Nash equilibrium to find the SPNE.
SPNE. Yeah, got it.
Okay,
So
so now
rollback equilibrium will be exists only one, you are coming to say, or like
yes, it will only happen here. Okay,
only in extension form. Yeah.
extensive form where all the information is available. Here the
Okay.
complete information is not there. Okay, so
Oh,
I'll
oh,
just
oh,
take this
oh, oh.
example only. 2222 BEC BE
3,1.
3,1
Yeah.
BED
E
BED 00
0 0. Yeah.
BFC is
0
zero
0.
zero, and this is
1,
1,
3.
and now you find the,
Best response. Like kind of.
so 2 2 2 2 1 3. Okay,
Yeah.
and when you do top 3,
3,
and this is
2,
2,
2.
and this is 2. So this, okay, you have got now
Nash equilibrium. Yeah.
AED,
Hmm.
AFD,
Yes.
and
And BEC.
BEC.
Yeah.
Now you have to check them one by one. So see,
Okay.
first check AED,
Hmm.
A, and this is coming from ED,
Yeah.
ED. Now tell
Yeah.
me, here one is there.
Hmm.
Will he play E 0
No,
0?
no. He won't. He
So,
won't.
so this is not a Nash equilibrium.
Not a Nash equilibrium.
AFD, AFD, yes, he will play. So this 1 3 which is there, it will come here 1 3,
Mm-hmm.
and it will come here also 1 3.
Yes.
Now here 1 3 and 2 2, what he will play? He'll play A, and
Yeah.
this has
Yeah.
come from DF. So AFD is
Yes.
a Nash equilibrium.
Yes. True.
Okay. Now we check another one. BEC.
Hmm.
BEC 3 1. 3 1 he will play.
Yes.
So 3 1 goes here.
Yeah.
Now A will play what? Okay. He will play B.
B. Yeah.
So BEC. So this is also Nash equilibrium.
Nash.
So, so this we have eliminated.
Yeah.
So
And
the
this I got it. Yeah.
okay. So the steps are what? First you find the normal form Nash equilibrium, and then
Yeah.
one by one check whether, okay, they're applicable or not.
But rollback equilibrium here we can't find out anything, right?
No.
Okay.
Here we cannot find.
Okay. Okay. Then IESDS only. So IEWDS gives unique Nash equilibrium, right?
IESDS, yes. IESDS will always give unique any.
Okay. But WDS will give some duplicates and all, right? Which
Yes,
is
yes.
not.
There might be some other Nash equilibrium also.
Okay.
Yes.
Okay. Got it.
Aditya, question, some
Yeah,
question?
sir. This was the question I was asking only.
Okay. So this is clear now?
Yes, sir.
Okay.
I was confused only in how the table was made because I was not getting the notation really
Okay.
and the nice equilibrium.
Yes. Chalo फिर okay. Thank you for joining. Have a nice
Thank
day.
you. Thanks a lot.
Okay.
All the best.
All the very best. Bye bye. Take care.
Bye.